Real numbers. Easy explanation. This chapter explains real numbers, especially prime factorization, HCF and LCM, rational numbers like root 2 and root 3. What is fundamental theorem of arithmetic? Every composite number can be expressed or written as a product of prime numbers in a unique way. For example, 60 can be written as 2 into 2 into 3 into 5. That is 60 is equal to 2 square into 3 into 5. So we can say that this 60 is a composite number. A composite number should always be expressed as the product of prime numbers. Then only we can say that the number is a composite number. And this is called prime factorization. Prime numbers have only two factors: 2, 3, 5, 7, 11. Which are the two factors? Yes, 1 and the number itself. Then composite numbers 4, 6, 8, 10, which can be expressed as the product of prime numbers. Example of prime factorization. Take 140, divide by smallest prime repeatedly. 140 is equal to 2 into 70, 70 is equal to 2 into 35, 35 is equal to 5 into 7. 140 is equal to 2 square into 5 into 7. Okay, we can say that 140 is a composite number and we can express it as product of these prime numbers, that is 2 square into 5 into 7. HCF and LCM. HCF, highest common factor. Take the smallest powers of common primes. 12 is equal to 2 square into 3. 18 is equal to 2 into 3 square. And common primes. The common primes in here is 2 and 3. Smallest powers 2 raised to 1 into 3 raised to 1, that is 6. Hence HCF is equal to 6. Always remember HCF, the full form of HCF is highest common factor. But highest common factor, so we are writing the prime factorization method, so we have to know that since it is common factor, highest common factor, we have to select only common factor. For example, in 12 and 18 the common factors are 2 and 3, so we have to take both 2 and 3. And from selecting this common factors, what we have to take care is we have to take the lowest common factor, because in 12 there is 2 square and in 8 there is 2. So this 2 is common, but when we are taking for HCF, we should take only the lowest factor. That is, in 2 square and 2 we are selecting 2, and from 3 and 3 square we are selecting 3. That's why the HCF is written as 2 into 3, that is 6. Next is lowest common multiple, LCM. Take the greatest powers. LCM is equal to 2 square into 3 square. From the same example, we are taking LCM. For LCM, we are taking the highest value, that is 2 square is taken. 2 square, and from this 3 square is taken. And there is no such consideration that it should contain common prime factors. If there is, for example, if there in case of 12 there was another number and we are writing the prime factorization as 2 square into 3 into 5, and in 18 there is no 5, so 5 is not common. but while writing LCM you have to multiply it with that 5 also. Important formula: HCF into LCM is equal to product of numbers. Very important. Many previous year questions has been asked from this area. For example, 12 and 18, 6 into 36. 6 was HCF and 36 was LCM is 216. And while multiplying 12 into 18 also, we will get 216. Next category is irrational numbers. Numbers that cannot be written as P by Q, where P and Q are integers. Example, root 2, root 3, root 5, pi. These all are examples for irrational numbers. Proof that root 2 is rational. Before going to this section, we need to know explain rational, irrational, whole, natural, real. Example. Types of numbers. All these numbers belong to the real number system. Number system mind map. In rational numbers includes integers and fractions and terminating or repeating decimals. And this integers includes whole numbers, natural numbers, negative integers, etc. Natural numbers. These are counting numbers. 1, 2, 3, 4, 5. Example 7, 25, 100. Used for counting objects, age, number of students, etc. Here the main important point is there is no 0. So 0 is not a natural number. Natural number can be used for counting. Since 0 is not used for counting, it is not a natural number. And in whole number, 0 is there. Whole means full. So including 0, that is 0 plus natural numbers is whole numbers. 0, 1, 2, 3, 4. Example 0, 12, 98. Important. No negative numbers include 0. So in natural numbers also there is no negative numbers, there is no fractions, there is no integers, etc. Positive integers are there, not integers are real number. These natural numbers are there, and these natural numbers plus 0 is whole numbers. And integers is whole numbers plus negative numbers, that is 0, 1, 2, 3, 4, etc. Also there will be the minus of these positive natural numbers, that is minus 3, minus 2, minus 1, 0, 1, 2, 3. Examples are integers. Example minus 8, 0, 45. Used in temperature, profit and loss, elevations, etc. And next coming to rational numbers. Numbers that can be written in the form P by Q and Q not equal to 0, where P and Q are integers, are called rational numbers. So rational numbers should be expressed in the form P by Q, in that P and Q are integers and Q not equal to 0. That are the two conditions that should specify. For examples, 1 by 2 minus 7 by 3. 5 is 5. When a question is asked whether 5 is a rational number, yes, 5 is a rational number, because 5 can be expressed as 5 divided by 1. So it can be expressed in the form of P by Q. So 5 is also a rational number. And 0.75. 0.75 is also a rational number because it can be expressed in terms of 3 by 4. And 0.333, that is also repeating, because that is also a rational number because it can be written in the form 10 by 3. Not 10 by 3, 1 by 3. So 1 by 3 is, when we calculate the 1 by 3 value, then we will get that 0.3333. So it is repeating. So it is also a rational number. Decimal property. Rational numbers have terminating decimals. Example 0.5 to 0.75. Repeating decimals. Example 0.666. Okay. For decimal numbers, it should be a rational number when it specifies or match two categories. Very simple. First one is terminating decimals. That means it should end. For example, 0.5. 0.5 is 1 by 2. Nah? 1 by 2 it can be expressed in terms of p by q. That is 1 by 2. When we calculate 1 by 2, you will get an answer of 0.5. After 0.5 there is no decimal digits. So it is terminated. So we can say that 0.5 or 1 by 2 is a rational number. And in the same case 2.75. 2.75 can be written as 275 divided by 100. When we calculate it also, we will get a round terminated figure, that is 2.75. After 75 there is no further digits are coming, so it is terminated. So we can say that whenever these terminating decimals are there, we can say that that number is a rational number. And when case of repeating decimals also, it is a rational number. For example, 0.666. Also we have seen that 0.333, that is 1 by 3. When we do 1 by 3, what will happen? The answer will be 0.333. That is repeating in a specific pattern. That is after 3, again 3, then also 3. So such repeating decimals and also terminating decimals are rational numbers. And coming to the opposite, that is non-terminating and non-repeating decimals are irrational numbers. And coming to irrational numbers that cannot be written as p by q, and their decimals never end, that is non-terminating, and never repeat. They will not repeat again. Example is root 2 and pi and root 5. Such digits are irrational numbers because they cannot be written in the form p by q. For example, root 2 is equal to 1.41421356, etc. There is no particular digit ending for this root 2 value. So it is non-terminating. The digits continue forever without repeating. So it's a rational number. And real numbers, all rational and irrational numbers together are called real numbers. So what are real numbers? This chapter's name is real number. That means all rational number plus irrational number. Example, 5 minus 3, 7 by 8, root 2, 5. All examples of real numbers. Real number line. Every point on the number line represents a real number. Table. Natural number 1, 2, 3 counting numbers. Whole number natural plus 0, 0, 1, 2. Integers positive, negative and 0, minus 2, 0, 5. Rational can be written as p by q, 1 by 2, 0.75. Irrational, non-terminating, non-repeating, that is root 2, pi, etc. Real, rational plus irrational, that is all the above figures can be called as real numbers. Easy trick. Natural, whole, integers, rational, real. Rational plus irrational, real. This is a symbol of set or subset. Natural numbers are a subset of whole numbers. Whole numbers are a subset of integers. Integers are a subset of rational numbers. Rational numbers are a subset of real numbers. Every natural number is a whole number. Yes, every natural number is a whole number, but all whole numbers are not natural numbers, because all whole numbers there will be 0, but there is no 0 in the natural number. Every whole number is an integer. Every whole number, that means 0, 1, 2, 3 are integers, but every integers are not whole numbers, because in every integers there come negative values, but in whole numbers there is no negative values. Every integer is rational, right? Also, rational plus irrational is equal to real numbers. And while coming to the NCERT textbook, there are certain exercises that are given in the textbook. First of all, root 2 is rational. We are proving that root 2 is rational. So coming to here, let us assume to the contrary that root 2 is rational. Okay. First we are assuming that root 2 is rational. Root 2 is rational. So we can find integers r and s such that root 2 is equal to r by s. What is the condition for this rational number? Rational number can be expressed in terms of p by q, p or q, or here it is shown that r and s. Here r and s should be integers and s not equal to 0. Suppose r and s have a common factor other than 1, then we divide by the common factor to get root 2 is equal to a by b, where a and b are coprime. Okay, then we are writing root 2 is equal to a by b, and where a and b are coprime. What do we mean by coprime number? That is, this a and b should not contain common factor other than 1. So b is equal to root 2a, cross multiplying, b is equal to root 2a. Squaring on the both sides and arranging, we get 2b square is equal to a square. Therefore 2 divides a square. Now by theorem 1.2 it follows that 2 divides a. What is theorem 1.2? Let p be a prime number if p divides a square, then p divides a, where a is a positive integer. That is theorem 1.2. That means if p is a prime number, for example 2, 3, 5, 7, etc., and this p if divides a number a square, then we can say that that prime number p divides a also. For example, p is 2 and a is 4, then we can say that 2 divides 4 square. That implies 2 divides 4 also. Okay. So by theorem 1.2 it follows that 2 divides a. So we can write a is equal to 2c for some integer c. Now we are giving the value for a is equal to 2c for some integer c. For substituting for a, we get 2b square is equal to 4c square. We are substituting this value to this value. Then we will get that 2b square is equal to 2c the whole square. That is 2b square is equal to, for a we have find a value 2c the whole square. That implies 2b square is equal to 4c square. That is written here. That is b square is equal to 2c square. This means that 2 divides b square. Since b square is equal to 2c square, we can say that this b square can be divided by 2. So by theorem 1.2 we can again say that if b square is divided by 2, then b is also divided by 2. So 2 divides b also. This means that 2 divides b square, and so 2 divides b. Again using theorem 1.2 with p is equal to 2. Therefore a and b have at least 2 as a common factor. So from this we can get the fact that here we said that 2 divides A, and here we can say that 2 divides B. From both this 2 divides A, here 2 divides B. But first we have taken assumption that root 2 is equal to A and B, where A and B are co-prime. Co-prime means they only have 1 as a common factor. But now when we coming to this section, we have find that 2 divides A and 2 divides B. That is, A and B have a common factor 2 other than 1. So this contradicts the fact that A and B are co-prime. This contradicts the fact that A and B have no common factors other than 1, means that is they are not co-prime. This contradiction has arisen because of our incorrect assumption that root 2 is rational. So we conclude that root 2 is irrational. Okay. And in this way we can prove that root 2 is irrational. And in the same way we have proven root 3 is irrational. That is, let us assume to the contrary that root 3 is rational. Okay, let us assume that root 3 is rational. Then we can write root 3 in form p by q. Here it is a by b, or any form we can write. For example, in the test it's given that a by b, so we can write root 3 is equal to a by b, where b not equal to 0 and a and b are integers. Also a and b are co-prime, that is, they do not have factor other than 1. Thus we can have find integers a and b, b not equal to 0, such that root 3 is equal to a by b. Suppose a and b have a common factor other than 1, then we can divide by the common factor and assume that a and b are co-prime. So by cross multiplying we will get root 3b is equal to a. Then squaring on both sides and rearranging, we will get 3b square is equal to a square. This proves that, this shows that this 3 can be a square is divisible by 3. Since 3 divides a square, 3 also divides a by theorem 1.2. A square is divisible by 3. By theorem 1.2 it follows that a also divisible by 3. So we can write a is equal to 3c for some integer c. Okay, substituting this value of a is equal to 3c in this equation. So we will get that 3b square is equal to 3c the whole square. That implies 3b square is equal to 9c square. This 3 is cut and b square is equal to 3c square. Here we got that b square is equal to 3c square. This means that b square is divisible by 3, so b is also divisible by 3 with b is equal to 3. Therefore a and b have at least 3 as a common factor. But this contradicts the fact that a and b are co-prime. This contradiction has arisen because of our incorrect assumption that root 3 is rational. So we can say that root 3 is irrational. This is an important question that will be asked in the Cbse board exam. Now we can go to the exercises. Exercise 1.2. Prove that root 5 is rational. Assume that root 5 is equal to a by b, where a and b are co-prime integers. Squaring on both sides, 5 is equal to a square by b square. Therefore a square is equal to 5b square. So a square is divisible by 5. Therefore a is also divisible by 5. Then we will give value to a. because since a is divisible by 5, we can say that a is equal to 5c. Substituting this in this, we will get 5c square is equal to 5b square. Therefore 225c square is equal to 5b square, 5c square is equal to b square. So b square is divisible by 5, hence b is divisible by 5. Thus both a and b are divisible by 5, which contradicts the fact that they are co-prime. Therefore this root 5 is rational. And coming to the next question, there is a question that is given in the NCERT, where you can see that show that 5 minus root 3 is rational. Here also we are taking that, let us assume to the contrary that 5 minus root 3 is rational. Thus we can find co-prime numbers a and b not equal to 0, such that 5 minus root 3 is equal to a by b. Therefore 5 minus a by b is equal to root 3. We are interchanging this to this side to avoid the negative sign. 5 minus a by b is equal to root 3. Rearranging the equation, we will get that root 3 is equal to 5b minus a by b. Since a and b are integers, we get 5 minus a by b is rational. And so root 3 is rational. Here we can say that 5 is a rational number, and we also imagine that a by b. So a by b is also a rational number. 5 minus, so this 5 is a rational number, this a by b is also a rational number. So a rational number minus another rational number is a rational number. So we will get it as root 3 is rational. Since a and b are integers, we get 5 minus a by b is rational, and so root 3 is rational. Because we already proved that root 3 is irrational. In the question, if it is of 3 mark, then we only need to prove that 5 minus root 3 is rational, or it may be said in the question that prove that 5 minus root 3 is irrational, provided root 3 is irrational. In some times, if 5 mark question, there will not be given that root 3 is irrational in the question. So we have to first prove that root 3 is irrational, then come to this question, and we have to prove that 5 minus root 3 is also irrational. So coming to the balance of the question, but this contradicts the fact that root 3 is irrational. This contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational. So we conclude that 5 minus root 3 is irrational. So coming to the next question, show that 3 root 2 is irrational. Root 2, okay. Let us assume that 3 root 2 is rational. Then we can write 3 root 2 is equal to a by b, where a and b are integers, b not equal to 0, also a and b co-prime. So we can write root 2 is equal to a by 3b. Since a by b is rational, this 3b means 3 into b. B is a integer. So this is a rational number. So coming to here, since 3a and b are integers, a by 3b is rational, and so root 2 is rational. So coming to here, a by 3b, since 3a and b are integers, this a by 3b will become a rational number. So this contradicts the fact that root 2 is irrational. Sorry, root 2 is rational. This is here it is irrational itself. This is due to our wrong assumption that three root 2 is rational. So our assumption is wrong. 3 root 2 is irrational. Okay. And in the same way we have to do the other questions also. Prove that root 5 is irrational. Let us assume that root 5 is rational. Then root 5 can be expressed in p by q, where p and q are integers, q not equal to 0. Also p and q are co-prime numbers. By squaring, 5 is equal to p square by q square. Therefore 5q square is equal to p square. 5 divides p square. Therefore 5 also divides p. By theorem 1.2 we know that if a integer divides another another square of the number, if for example any integer say p divides another integer square of the another integer p square, then that divides that p also. Now we can write it as since 5 divides p is equal to 5a for some integer, a is some integer. By substituting this value, this is 2, this is 1. Substituting 2 in 1, we will get 5q square is equal to 5a the whole square. That implies 5q square is equal to 25a square. and cutting this 5, q square is equal to q square is equal to 5a square. Therefore 5 divides q square. Therefore 5 also divides q. This is 3. From here we can say it as here we can give it as 3, 3. Here 2. From 2 and 3 here 4, 2 and 4, we can say that this is what 5 divides p, here 5 divides q. P and q have a common factor factor 5 other than 1. This contradicts the fact that P and Q are coprime. This contradiction occurred due to our wrong assumption that root 5 is rational. Therefore, our assumption is wrong. Root 5 is irrational. Okay. Then coming to the next question, 3 plus 2 root 5 is irrational. Three plus 2 root 5. Let us assume that 3 plus 2 root 5 is rational. Then we can write 3 plus 2 root 5 is equal to a by b, where a and b are coprime, b not equal to 0, and a and b are integers. 2 root 5 is equal to a by b minus 3. That is, root 5 is equal to a by 2b minus 3 by 2. This is a rational number. This is also a rational number. So a rational number minus a rational number is a rational number. We get it as root 5 is rational. This is wrong because root 5 is irrational. We get to this wrong contradiction because of our wrong assumption, as 3 plus 2 root 5 is rational. So 3 plus 2 root 5 is irrational, as we are writing it in the same format. Now coming to the next question. Here also we have taken as root 5 is irrational and it is provided in the question. For example, if it is given as a 5-mark question and it is not given that Whenever the previous year questions are asked from this section, it is last year also there was one question like this, that is 3 plus 2 root 5 is rational. We have to prove that 3 plus 2 root 5 is irrational, and in the question itself, board exam question, there will be given that, provided it is given that root 5 is rational. So root 5 is irrational. So we only have to prove that 3 plus 2 root 5 is irrational, because in the question root 5 is rational is given. But in 5-mark question, sometimes there will be not given this root 5 is irrational, it will not be given. So in that question, if it is a single line asking that prove that 3 plus 2 root 5 is irrational, you have to first prove that root 5 is irrational. Then you have to prove that 3 plus 2 root 5 is irrational. Okay, then coming to the next question, prove that the following are irrationals. 1 by root 2. Let us assume that 1 by root 2 is rational. Then we can write 1 by root 2 is equal to a by b, where a and b are integers, b not equal to 0, and a and b are co-prime. Then we can write it as root 2 is equal to b by a. This is a rational number. Therefore, since b by a is a rational number, root 2 is also a rational number. But this contradicts the fact that root 2 is rational. This wrong contradiction occurs due to our wrong assumption that 1 by root 2 is rational. So our assumption is wrong. Therefore 1 by root 2 is irrational. Coming to the next question, it's 7 root 5. 7 root 5 also, 7 root 5 is written as a by b. So root 5 is equal to a by 7b. This is also in the same format. You have to write that a by 7b is rational. So root 5 is rational. This contradicts the fact that root 5 is rational. So our assumption is wrong. So this 7 root 5 is irrational. And then coming to the next question, 6 plus root 2. This also, first we have to write in the same steps. 6 plus root 2 is equal to is a rational number. Then 6 plus root 2 is equal to a by b. And then root 2 is equal to a by b minus 6. The 6 is also a rational number, and a by b is also a rational number. So a rational number minus a rational number is a rational number. So this gives that root 2 is also rational. This is wrong because root 2 is rational. This wrong contradiction occurs due to our wrong assumption that root 2 is 7 root 5 is rational. So our assumption 7 root 5 is rational is wrong. So 7 root 5 is irrational. Here also have 3 plus 2 root 5. 2 root 5 is equal to 3 plus 2 root 5 minus 3. Rational. Here ChatGPT does not have the feature to write a by b for fractions. That's which is given us this monitor. Here instead of R, we have written A by B or P by Q, but in ChatGPT they have given instead of P by Q, instead of A by B, they are given R, and that R is a rational number. Here 1 by root 2 is equal to R, therefore 1 is equal to R root 2, root 2 is equal to 1 by R. Since 1 is rational, R is rational, 1 by R is also rational, thus root 2 becomes rational. But we know root 2 is irrational, contradiction, therefore 1 by root 2 is rational. Prove that 7 root 5 is irrational. Assume 7 root 5 is rational, let 7 root 5 is equal to R, where R is rational. Divide both sides by 7. Root 5 is equal to R by 7. Since R is rational, 7 is rational, R by 7 is rational. Therefore, root 5 becomes rational, but root 5 is irrational. Contradiction. Since 7 root 5 is rational. Prove that 6 plus root 2 is irrational. Assume that 6 plus root 2 is rational. Let 6 plus root 2 is equal to R, where R is rational. Subtract 6 from both sides. Root 2 is equal to R minus 6. Since R is rational, 6 is rational, their difference is rational. Thus root 2 becomes rational. But root 2 is irrational. Contradiction. Therefore 6 plus root 2 is irrational. Okay. Then there is the summary provided in the last. The fundamental theorem of arithmetic: every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors were. If P is a prime and P divides A square, then P divides A, where A is a positive integer. To prove that root 2, root 3 are irrational. That's very important. And one note is also given that HCF of PQR into LCM of PQR is not equal to P into Q into R, where PQ R are positive integers. However, the following results hold good for three numbers PQ and R. LCM of three numbers PQR is equal to this product of three numbers PQR into HCF of that three numbers divided by HCF of PQ, HCF of QR and HCF of PR. And in the same way, when coming to this, HCF of three numbers PQR is equal to product of three numbers P into Q into R into LCM of P, Q and R divided by LCM of PQ, LCM of QR and LCM of PR. Okay, let's, before coming to the revision questions, we have to look to NCERT. There we have studied here LCM of 3 numbers and HCF of 3 numbers. How to find out a particular value? We can take an example for this. For example, if we are taking 2, 3 and 4 as examples. For this, LCM of PQR is equal to 2 into 3 into 4 into HCF of 2, 3, 4 is 1 because they do not have common prime factors. Divided by HCF of P and Q is 1, HCF of Q and R is 1, and into HCF of P and R. HCF of P and R is 2. So you will get it as 3 into 4, 12 as LCM. Two, 3 and 2 square. Here if we get the LCM as normal way, we will get 2 square into 3. That is 4 into 3, 12. It's right. And now coming for HCF, P into Q into R, 2 into 3 into 4 into LCM of PQR is 12 divided by LCM of PQ. LCM of these two numbers is 2 into 3. This 6 into LCM of Q and R, 3 and 4 is 12 into LCM of P and R, 2 and 4, LCM is 2 and 2 square, LCM is 2 square, that is 4. 4 is 4, 12, 12, 6, 6, HCF is equal to 1. So here also by normal way we know that 2, 3 and 4 there is no common factors. So we can say the HCF of these 3 numbers is 1 and LCM is 12. So this formula you have to by heart. Sometimes there may be chance that questions can be asked from this formula. Now we can do one by one questions. What is a prime number? Prime number examples are 2, 3, 5, 7, 11, etc. That is, they do not have any other factors other than 1 and that number also. Is 1 a prime number? No, 1 is not a prime number. Write the prime factorization of 24, 90, 144. Okay. (24, 90 and 144) prime factorization. 24, 2, 12, 6, 2, 6, 2, 3. Therefore 24 is equal to 2 cube into 3. Next 90. 3, 2, 45. 3, 1, 5. 3, 5. Therefore 90 is equal to 2 into 3 square into 5. Then 144. 2, 72. 2, 36. 2, 18, 2, 9, 3, 3. 144 is equal to 2 raised to 4 into 3 square. Next question, find the HCF of 12 and 18. Okay. HCF of 12 and 18. 12, 2, 6, 2, 3. So 12 is equal to 2 square into 3. Next is 18, 2, 9, 3, 3. 18 is equal to 2 into 3 square. So HCF is highest common factor. So there should be common factor. So here the common factors are 2 and 3, and here high. So we have to take lowest number. So in the common factors, 2 square and 2, the lowest is 2, and in 3 and 3 square, lowest is 3. Therefore 2 into 3, 6. Next, HCF of 24 and 36. HCF of 24 and 36. 24, 36. 24, 2, 12, 2, 6, 2, 3. 24 is equal to 2 cube into 3. Next is 36. 2, 18, 2, 9, 3, 3. 36 is equal to 2 square into 3 square. So HCF is highest common factor. So common factor should be there. 2 cube and 2 square. 2 and 3 are common factors. And highest. So we have to take lowest of the common factor. So lowest is in 2 square and 2 cube. Lowest is 2 square into 3 and 3 square. Lowest is 3. Therefore 4 into 3 is equal to 12. So 24 and 36, HCF is 12. Next question is find the LCM of 15 and 20. LCM of 15 and 20. 15, 20 LCM. 15, 3, 5, 20, 2, 10, 2, 5. So coming to this LCM, lowest common multiple. Here we designate common factor, and since it is lowest, we will take the high value. 3 is there. In 2 The highest value is 2 square into 1 3 is there and 5 is there. So 4 into 3 into 5 is equal to 12 into 5 60. Yes. Next is 18 and 24. 18 24. 18 2 9 3 3. 24 2 12 2 6 2 3. So for 18 is equal to 2 into 3 square and 24 is equal to 2 cube into 3. So LCM is lowest common multiple. So no need of common factors. All factors should be taken, but from that taken highest value. 2 and 2 cube, highest is 2 cube into 3 and 3 square, highest is 3 square. Therefore 2 cube 8 into 3 into 2, 3 into 3 9, 3 into 9 72. Yes. Next question is 91 a prime number? 91. 91 a prime number. 91 can be expressed in terms of 17. 17 into 3. Sorry, 17 into 5 is 85. 7 no 17 19 19 into no 19 can be 13 13 into 7 21 2 91. So 91 can be written as 7 into 13. It can be expressed as the product of prime numbers. So this 91 is a prime number. So it has factors other than 1 and 91. Is 91 a prime number? No, it is a composite number. State the fundamental theorem of arithmetic. Every composite number can be expressed as the product of its prime numbers. Every composite number can be expressed as a product of primes uniquely except for the order. Define irrational number. A number that cannot be written in the form p by q, where p and q are integers and q not equal to 0. Examples for irrational numbers: root 3, root 5, 2 root 2, 1 by 2 root 2, 3 plus 2 root 5, 5 minus 2 root 3, etc. Is root 49 is irrational? Root 49 is equal to 7. It is rational. One rational and one irrational number. Rational example is 3 by 5 and irrational example is root 7. 2 mark answers. Prime factorization of 156. Two, 7, 8, 2, 39, 3, 1, 3. Therefore 156 is equal to 2 square into 3 into 13. Five 005. Five 1001. Is it divisible by 7? 1 30. 4 21 3. Now 13 into 11, 13, 13, 3, 4, 3, 1, 4, 3, 13, 11. So 5005 can be expressed as 5 into 7 into 13 into 11. 5 into 7 into 11 into 13. HCF and LCM of 8 and 12. Eight, 12. 8 is equal to 2 into 2 into 2, and 12 is equal to 2 into 2 is 6, 2 into 3. So HCF is highest common factor. That means common factors should be there. What is a common factor? 2 is only the common factor. That is 2 cube and 2 square is the common factor. And highest, so we have to take the lowest of them. That is 2 square. Here 2 cube, here 2 square into 3. Only common factors is 2, and looking at their powers we have to take the lowest, that is 2 square, that is 4. And LCM also we have to find. LCM is equal to lowest common multiple. Here it is lowest, so we have to take highest of all. Here highest of 2 cube and 2 square is 2 cube and 3. 2 cube is 8, 8 into 3, 24. Yes. Now 18 and 30. 18 and 30. 18, 2, 9, 2, sorry, 3, 3. So 18 is written as 2 into 3 square. And coming to 30, 2, 15, 3, 5. Written as 2 into 3 into 5. HCF. HCF is highest of the common factors. Here common factors we have to look for. Common factor is only 2 and 3 is there, and from the powers of it we have to take the lowest. In 2 and 2 there is only 1, 2, and in 3 square and 3 the lowest is 3. 2 into 3 is equal to 6. And similarly LCM, lowest common multiple, we have to take all the factors, not only common factors. Here in 2 and 2 we will take 2. 3 square and 3 we will take the highest, 3 square into 5. This 2 into 5, 10, 10 into 6, 10 into 9, 90. And 6. Yes. Verify formula for 16 and 24. Okay, 16 and 24 we have to verify their formula of multiplication. 16 and 24. 16, 24. First you have to find the LCM. 16, 2, 8, 2, 4, 2, 2, 24, 2, 12, 2, 6, 2, 3. So 16 is equal to 2 raised to 4, and 24 is equal to 2 cube into 3. To find HCF is equal to highest common factors only 2, and in that we have to take the lowest power, that is 2 cube. And LCM we have to take full, and here in 2 raised to 4 and 2 raised to 3 we have to take highest, 2 raised to 4 into 3. here it is 8, and here it is 16 into 3, 32, 48. So HCF into LCM is equal to 8 into 48 is equal to 48 into 8 is equal to 64, 4 into 8, 32, 38, 384. And we have to look for the product of the two numbers, 16 into 24. 16 into 24 into 64 and 32. Here also 384. So product of two numbers, 16 into 24 is equal to 384. LHS is equal to RHS. Okay. Next question, can 6 raised to n end with 0? Similar type questions are so much asking in the board exam. So coming to this type of question, here we can write 1 raised to n. So 1 raised to 1, 1 into 1, 1, 1 cube, 1 into 1 into 1, 1, 1 into 1 into 1 into 1 is also 1. And in 2 raised to n we will get 2, 4, 2, then 2 square 4, 2 cube 8, 2 raised to 4 16, 2 raised to 5 32, 64, 128. Here 3 raised to n, 3, 9, 27, 64, 128, 128, 64 into 3, 243. Then 4 raised to n, 4, 16, 64, 256, 5 raised to n, 5, 25, 125, 6 raised to n, 6, 36, 216, 7 raised to n, 7, 49, 49 into 7, 243, 243 into 7, 2, 2 balance, 14, 16, 1691, 1691 into 7, 7, 9 into 7, 63, 6 balance, 16 into 7, 56, 62, 6 balance, 13, 13237. 13237. Okay, then coming to 8 raised to n, 8, 64, 64 into 8, 2, 3 balance, 8, 51, 512, 512 into 8. 16 plus 9, 8 into 5, 40, 4096 into 8, 48, 4 balance, 76, 7, 32, 32768. Then 9 raised to n, 9, 81, 81 into 9, 9, 729. So you can see that 1 raised to n always end with a 1. For 2 raised to n it will end with 2, 4, 8, 60. Then repeat. That is, it will end with 2, 4, 8. Then for 3 raised to n it will end with 3, 9, 27, 64. Then similar pattern occurs with the 243 where 3, then 9, similar patterns request. And for 4 raised to n, 4, 6, then 4, 6. And for 5 raised to n, 5, always end with 5. And 6 raised to n, always end with 6. And 7 raised to n, it end with 7, 9, 3, then 1, then repeat. And for 8 raised to n, it end with 8, 4, 2, 6, then pattern repeats. For 9 raised to n, 9, 1, then pattern repeats, 9. To prove that 6 raised to n doesn't end with digit 0, we have to write that 6 raised to n is equal to 2 into 3 the whole raised to n. If 6 raised to n ends with the digit 0, it must be divisible by 5, or 6 raised to n should contain 5 as its factor. But 6 raised to n is equal to 2 into 3 the whole raised to n. It doesn't contain 5 as a factor. So we can conclude that 6 raised to n does not end with digit 0. Okay. 6 raised to n is equal to 2 into 3 the whole raised to n. No factor 5 exists. A number ending with 0 must contain 2 into 5, hence impossible. Y is 7 into 11 into 13 plus 13 composite. Seven into 11 into 13 plus 13. When taking 13 as common, 13 is equal to 7 into 11 into 1 plus 1. That is 13 is equal to 77 plus 1. This 13 into 78. This 13 into 478 we can write as 239, 213, 2 square into 13. Hence it is composite. Sorry, here it is 3, 1, 3, 2 into 13 into 3. We can write it as a product of prime numbers. So we can say that 7 into 11 into 13 plus 13 is composite. Prove that 5 root 2 is rational. Sorry, 5 plus root 2 is rational. In this question we can assume that root 2 is rational. So we can write 5 plus root 2 is equal to a by b. First step is 5. Let us assume that 5 plus root 2 is rational. So we can write 5 plus root 2 is equal to a by b, where a and b are integers, b not equal to 0, and a and b have only one factor, that is 1, or a and b are co-prime. So we can write root 2 is equal to a minus a by b minus 5, or is equal to a minus 5b by b. This 5 is a rational number and a by b is also a rational number. A rational number minus a rational number is a rational number. This says that root 2 is rational. But this contradicts the fact that root 2 is irrational. This contradiction occurred due to our wrong assumption that 5 plus root 2 is rational. So 5 plus root 2 is irrational. Plus root 2 is irrational. True for root 3 irrational. This is also in the same way. For root 3. Let us assume that for root 3 is rational. So we can write for root 3 is equal to a by b, where a and b are integers, b not equal to 0, and a and b are co-prime. So we can write 4 by root 3 is equal to a by b. Therefore root 3 is equal to a by 4b. A by 4b is rational. So we will get that root 3 is also rational. But this contradicts the fact that root 3 is irrational. We get the we get this wrong because of our wrong assumption that 4 root 3 is rational. So 4 root 3 is irrational. Assume rational, divide by 4. This is incomplete. Then 3 mark answers. HCF and LCM of 70 and 120. $72 and 120. Three, 122, 60, 30, 50, 5. So 72 is equal to 2 cube into 3 square, and 120 is equal to 2 cube into 3 into 5. We have to find both LCM and HCF. HCF, highest common factor. Common factors is 2 raised to 3 and 2 and 3. From this highest common factor, so we have to take lowest power. This in 2 raised to 3 and 2 raised to 3, there is 2 raised to 3 and 3 square and 3, the lowest is 3. 2 give 8 into 3, 24. Then coming to LCM. LCM is equal to 2 cube into 3 into 5. This 8 into 15 is equal to 120. Therefore 24 and 120. 24 and LCM is 360. No, it's wrong, because in 3 square and 3 we have to take the lowest. No, it's wrong. You have to take the highest value. So 2 cube into, sorry, there was a mistake. Here it is, we have to take 2 cube into 3 square. In 3 and 3 square we have to take the highest value, 3 square into 5. That is 2 cube into 9 into 5. That is 2 cube into 45. That is 8 into 45. 8 into 45. 45 into 8. 40 for balance 360. Therefore 360. The answer is 24 and 360. 24 and 360. Prove that root 3 is irrational. Let us assume that root 3 is irrational. So we can write root 3 is equal to a by b, where a and b are integers, b not equal to 0, and a and b are co-prime. So squaring, we will get that 3 is equal to, squaring we will get that 3b square is equal to a square. So 3 divides a square. This implies 3 also divides a. So we can write that a is equal to 3 r for some integer r, or 3c. Then substituting 3b square is equal to 9c square, cutting b square is equal to 3c square. So 3 divides b also, b square. So 3 also divides b. Thus both divisible by 3. There is a contradiction that a and b are co-prime. So we get this wrong due to our wrong assumption that root 3 is rational. So root 3 is irrational. Same way we can prove that root 7 is also irrational. Prove 3 plus 2 root 5 is irrational. This also same way, 3 plus 2 root 5. Plus 2 root 5. 5 is equal to a by b. Therefore 2 root 5 is equal to a by b minus 3. And when we get this 2 to here, 2 by 2. So a by 2b. 3 by 2 is already rational. A by 2b is also rational. So we will get that root 5 is also rational. But root 5 is irrational. We get this due to a wrong assumption that 3 plus 2 root 5 is rational. So our assumption is wrong. 3 plus 2 root 5 is irrational. Prove 1 by root 5 is irrational. It's also same. Root 5 is equal to 1 by r. Contradiction. Bell question. What is Bell's question? Last question. A bell rings every 12 minutes and another every 18 minutes. If both ring together now, after how many minutes will they ring together again? Here you have to find LCM. It's the same type of question that you have to do in our exercise. Like one person start to go around. We said then there is a circular field where is one will take 12 minutes, another will take 14 minutes. Similar type of question we have done in our exercise. It's a same model of the question. We know that a bell rings every 12 minutes and another every 18 minutes. There are two bells. One ring every 12 minutes and another ring at every 18 minutes. If both ring together now, after how many minutes will they ring together again? Eighteen and 12. Twelve, 18. Here, this is first bell, this is second bell. Now this is said that the bells rang together. So first time the first bell ring after 12 minutes, second bell will ring after 18 minutes, then the next will ring after 24th minute, then this will ring at 36th minute. Now this will first one will be at 36 and second will be at 54. Here we can see that first bell will ring after at 36 minute, at 12 minute it will ring, then at next one at 24th minute, next one at 36th minute. When this bell, first bell rings at the same time, second bell also rings. We can also find this by finding the LCM. 2, 6, 2, 3 and 18, 2, 9, 3, 3. LCM is equal to lowest common multiple. So every factor we should consider, and in every common factor we should take the highest value. So in 2 square and 2 we will take 2 square, and in 3 and 3 square we will take 3 square. That is 4 into 9, that is 36. So we can say that these bells together ring at the 36th minute. Board exam style questions. 3 students factorized 180 as 2 square into 3 square into 5, 3 square into 2 square into 5, 5 into 2 square into 3 square. Are all factorization correct? 2 square into 3 square into 5, here 3 square into 2 square into 5, A and B are correct. 5 into 2 square into 3 square. Yes, all factorizations are correct. Which theorem supports this? Theory of factorization. Theorem of factorization. Why is this theorem called unique? Because these all are prime numbers. They does not repeat. That's a good question. Bells ringing question, we got it as 36. MCQ answers. Case based. All Yes, all three factorizations are correct because 180 is equal to 2 square into 3 square into 5. Changing the order of factors does not change the product. Verification 180. Which theorem supports this? Fundamental theorem of arithmetic. Fundamental theorem of arithmetic supports this. Every composite number can be expressed as a product of prime numbers uniquely except for the order of the factors. So no, there is no consideration about the order. Order is accepted. Why is this theorem called unique? The theorem is called unique because every composite number has only one prime factorization. Only the order of prime factors may change. Okay. Only the order is changed. Balance this 180 have same or only unique composite number. Here 2 square into 3 square into 5. Here also 5 into 3 square into 2 square. Represent the same unique factorization of 180. Okay. Next questions. Assertion reason. Assertion. Root 2 is irrational. Wait for my answer. Root 3 is irrational. If a prime number divides a square, then it divides a. A is true. R is also true. But R does not explain A. B. The correct answer is A. Assertion is rational true because it cannot be written in the form. This question is little confusing. Let's look the next question. The LCM of two numbers is always divisible by both numbers. LCM of two numbers is always divisible by both numbers. Let's take 2 and 3. LCM is 6. LCM is 6. Yes, 6 is divisible by, yes, LCM itself means the lowest common multiple. So it's a multiple of both the numbers or all the numbers. So it is always divisible by both the numbers. LCM is formed by taking the greatest powers of all prime factors. Answer will be A. Yes. LCM of two numbers is always divisible by both numbers. True. LCM takes the greatest powers of prime factors. True. 36. Example 12 and 18. 12 2 square into 3, 18 2 into 3 square. LCM is equal to 2 square into 3 square is equal to 36. 36 is divisible by both 12 and 18. Yes. Assertion. Root 49 is irrational. No. Root 49 is 7. That is rational. 49 is a perfect square. 49 is a perfect square. A is false, R is true. A is false, R is true. D. No. Correct, okay. Assertion is irrational. 7 is a rational number. 49 is a perfect square. True. Since 49 is a perfect square, its square root is rational. Therefore, correct answer is D. And today's session is completed. We have completed the 2-hour session. Balance session we have take on the next day.